of the equation. So when you put them together, you will end up, when you put them equal, you will end up with the same equation, and therefore you will get the equivalence between the inertial and the gravitational. Because if you think about these two terms, one of them is related to the gravitational and the other is related to the inertial. And maybe this will be more clear even when we go to the next, which is getting the same thing almost, but not from complex momentum, but from complex energy, because as I told you before, even energy now becomes complex and multidimensional. So let me again skip this to save some time. And therefore, if you derive, you remember that the force is actually the derivation of momentum per time. However, because the momentum is conserved, and remember the momentum is conserved even when the velocity changes, because this is complex momentum, not normal momentum. Normal momentum, of course, if you have motion, you have change of velocity, and therefore you don't have conservation of momentum. You have conservation if you have collision between different particles, but I mean here for the same particle, if the velocity of the particle increases, the momentum will increase. However, for the complex momentum, it will be always conserved even when you accelerate, even when you have a change of velocity. And that's because the change in the real part of the momentum will be compensated by the change in the imaginary part, and the total will be imaginary. The total will be zero. The difference in the total will be zero. And therefore the force will be also zero, because remember also the velocity is zero at every time. So in reality everything is zero. But this zero is the complex part, and therefore it has two parts. It has real and imaginary. So when you put them equal, not equivalent, because remember in the current, in the original thought experiment of the general relativity, we get the equivalence between the inertia and the gravitational through the Gedanken experiment of the space accelerator or the elevator. And we obtain this equivalency, we obtain it by induction. Here we are obtaining it by equation, and this is a very big difference, because here it's mathematics, it's exact derivation, and therefore it's no longer, they are equal. However, doing this derivation, which gives us zero, is really not very easy, because with this new fractal, I didn't really speak about this too much, because it's really a little bit different from our presentation today. But actually the new geometry is fractional or fractal, and therefore we cannot really perform this derivation using standard calculus, because this new geometry, it's no more differentiable at every point, and therefore you need to apply special rules which are very difficult to obtain now. And only here we get complications. As you have seen, until now we are using only classical mechanics, classical equations. But if you want to go through the details here, you need to really go through more complicated mathematics, which is beyond our lecture today. So time is running out very quickly. I'm now going to mention this final slide, I hope, which is the conservation of complex energy. Again, please read this by yourself. It's already, I think, understood. So you can do the same thing for energy, just like momentum. However, you'll see here minus, and this minus is in our time, it will be plus, because we consider that we are living in a real world, which is spherical, normal, complex, but it's actually here hyperbolic, and therefore it's half world, and therefore it's minus, and we have the supersymmetrical. Together will be positive. And actually this is yet another derivation, because if you follow this equation, you will get E equal mc square, like also a new method of deriving this fundamental equation.